In this video, we're going to continue our discussion of power series functions. Evaluate the integral x cubed divided by 2 plus x to the power of 5 dx as a power series. Part B. Use part A to estimate the definite integral from 0 to 0.5 x cubed divided by 2 plus x to the power of 5 dx accurate to within 10 to the power of minus 7. The hint here is to apply the alternating series test estimation theorem. Let's look at question 1a first. Let's first rewrite the integrand x cubed divided by 2 plus x to the power of 5. Let's rewrite this as x cubed times 1 divided by 2 plus x to the power of 5. Now let's factor out 2 from the denominator so we can get the pattern of a sum of a geometric series. So we have x cubed divided by 2 times 1 divided by 1 plus x to the power of 5 divided by 2. This is equal to x cubed divided by 2 times 1 divided by 1 minus x to the power of 5 divided by 2. So now we can see that we have the pattern of a geometric sum. The geometric sum formula is 1 over 1 minus x. This is a sum of a geometric series. This is equal to summation n equals 0 to infinity x to the power of n for absolute value of x less than 1. So let's replace x by minus x to the power of 5 divided by 2 into the geometric sum formula, and we will obtain x cubed divided by 2 plus x to the power of 5. This is equal to x cubed divided by 2 times 1 over 1 minus x to the power of 5 divided by 2. Now it is this part that is a sum of a geometric series that we're going to represent by a power series. So x cubed divided by 2, summation n equals 0 to infinity minus x to the power of 5 divided by 2 to the power of n. Now let's multiply x cubed divided by 2 inside the summation, and we're going to get summation n equals 0 to infinity x cubed divided by 2 times minus x to the power of 5 divided by 2 to the power of n. We get summation n equals 0 to infinity x cubed divided by 2 times negative 1 to the power of n x to the power of 5n divided by 2 to the power of n. We're simplifying the stuff inside the brackets, and now we simplify this a little bit further. We get summation n equals 0 to infinity minus 1 to the power of n. Now we have the same base. The base is x. We add up the exponents, so we get x to the power of 5n plus 3. And in the denominator, we have 2 times 2 to the power of n. We get 2 to the power of n plus 1. This is the power series representation of the integrand x cubed divided by 2 plus x to the power of 5. So we have the power series representation of the integrand x cubed divided by 2 plus x to the power of 5. This is equal to summation n equals 0 to infinity minus 1 to the power of n x to the power of 5n plus 3 divided by 2 to the power of n plus 1. Now let's integrate term by term to find the integral x cubed divided by 2 plus x to the power of 5 dx. So integral of x cubed divided by 2 plus x to the power of 5 dx. This is the integral of the power series. Integral of summation n equals 0 to infinity minus 1 to the power of n x to the power of 5n plus 3 divided by 2 to the power of n plus 1. Now integral of a sum is sum of the integrals, so we can rewrite this as summation n equals 0 to infinity minus 1 to the power of n divided by 2 to the power of n plus 1. These are constants. We push them outside the integral. And we integrate the term that involves x, because we're integrating with respect to x. X to the power of 5n plus 3 dx. We get summation n equals 0 to infinity minus 1 to the power of n divided by 2 to the power of n plus 1. Now reverse the power rule, add 1 to the exponent, and divide by the same. So we get x to the power of 5n plus 4 divided by 5n plus 4 plus c. We now have the power series representation of the integral x cubed divided by 2 plus x to the power of 5 dx. This is equal to summation n equals 0 to infinity minus 1 to the power of n times x to the power of 5n plus 4 divided by 2 to the power of n plus 1 times 5n plus 4 plus arbitrary constant of integration plus c. All right, so what we have is integral of x cubed divided by 2 plus x to the power of 5 dx. We found the power series representation of this integral. This is summation n equals 0 to infinity minus 1 to the power of n, x to the power of 5n plus 4 divided by 2 to the power of n plus 1 times 5n plus 4 plus c. Now let's expand term by term. So we have integral x cubed divided by 2 plus x to the power of 5 dx is equal to, plug n equals 0, we're going to get negative 1 to the power of 0, that's 1. We get x to the power of 4 divided by 2 times 4. Plug n equals 1, we get minus x to the power of 9 divided by 4 times 9. N equals 2, we're going to get x to the 14 divided by 8 times 14. 0, 1, 2, and put n equals 3. We're going to get negative 1 cubed, which is going to give us minus x to the power of 3 times 5 is 15 plus 4. That gives us 19 for the exponent. Divided by 2 to the power of 3 plus 1, 2 to the power of 4, that's 16. Multiplied by n equals 3 times 5 is 15 plus 4, that's 19. And so on. So this is an infinite series, and the sum of this infinite series represents this integral. So we have a power series representation of this integral. Now, let's talk about the radius of convergence of this integral. We know the original series, x cubed, the integrand, x cubed divided by 2 plus x to the power of 5 dx. So this was the integrand. This is equal to, we rewrote this as x cubed times 1 divided by 2 minus x to the power of 5 divided by 2. The reason for that is we wanted to write it as a sum of a geometric series so we can expand term by term and eventually integrate term by term. So in any case, this is a geometric series with the common ratio r is equal to this part, minus x to the power of 5 divided by 2. And for a geometric series converges when the common ratio, the absolute value of the common ratio is less than 1. So absolute value of minus x to the power of 5 divided by 2 is less than 1. Absolute value gets rid of the minus sign, so we get absolute value of x to the power of 5 divided by 2 less than 1. Simplifying this, absolute value of x to the power of 5 is less than 2. Take the fifth root of both sides, and we're going to get absolute value of x is less than 2 to the power of 1 over 5. And this is the radius of convergence, so capital R is equal to 2 to the power of 1 over 5. The interval of convergence is x less than 2 to the power of 1 over 5 and larger minus 2 to the power of 1 over 5. This is the interval of convergence, all the values of x for which the integral can be represented by a power series, and this is the radius of convergence. All right, part B is asking us to evaluate the definite integral from 0 to 0.5 x cubed divided by 2 plus x to the power of 5 dx. So to evaluate this integral, we're going to need to apply the fundamental theorem of calculus. So let's use the antiderivative that we derived earlier, except we'll just put c equals 0, because we can use any antiderivative. All right, so we have integral 0 to 0.5, x cubed divided by 2 plus x to the power of 5 dx. This is equal to x to the power of 4 divided by 8 minus x to the power of 9 divided by 36 plus x to the power of 14 divided by 112 minus x to the power of 19 divided by 304, and evaluated from 0 to 0.5. Of course, this goes on and on. It's an infinite series. So what we're really trying to do is to find an estimate for the definite integral accurate to 10 to the power of minus 7. So we're trying to estimate the value of this definite integral by using this power series. So let's apply fundamental theorem of calculus and plug the upper limit in and lower limit in. We're going to get 0.5 to the power of 4 divided by 8 minus 0.5 to the power of 9 divided by 36 plus 0.5 to the power of 14 divided by 112 minus 0.5 to the power of 19 divided by 304. This is an infinite series. Now the question here is, how many terms do we add up? We're trying to get the error, so the error is s minus sn, to be less than 10 to the power of minus 7. Now we know from the alternate series estimation theorem that if we add the first n terms, the error is less than n plus 1th term. So in this case, if we add the first 3 terms, the error is going to be less than the absolute value of the 4th term. So it suffices to look at the 4th term and to see whether this 4th term is less than, where the absolute value of this term is less than 10 to the minus 7. If the absolute value of this term is less than 10 to the power of minus 7, we can add the first 3 terms to estimate this definite integral. And the error of this approximation will be less than 10 to the power of minus 7. So let's do that. So we found the integral from 0 to 0.5 x cubed divided by 2 plus x to the power of 5 dx. This is equal to 0.5 to the power of 4 divided by 8 minus 0.5 to the power of 9 divided by 36 plus 0.5 to the power of 14 divided by 112 minus 0.5 to the power of 19 divided by 304. So let's look at the absolute value of the 4th term. Absolute value of the 4th term is equal to absolute value of negative 0.5 to the power of 19 divided by 304. This term here, the 4th term, we're finding its absolute value, and we calculate this, and this comes out to point with 4 zeros, 4 decimals, 4 zeros, another 3, so 7 zeros, and a 6. And this is definitely less than 10 to the power of minus 7. So that means we should add the first 3 terms. If we add the first 3 terms, the alternate series estimation theorem tells us that the error of approximation is less than the 4th term. And since the absolute value of the 4th term is less than 10 to the power of minus 7, our error will be less than 10 to the power of minus 7. So the integral from 0 to 0.5 x cubed divided by 2 to the power of x to the power of 5 dx. This is approximately equal to the sum of the first 3 terms of the power series. 0.5 to the power of 4 divided by 8 minus 0.5 to the power of 9 divided by 36 plus 0.5 to the power of 14 divided by 112. Let's add up these 3 terms. So if we add these 3 terms, we're approximating this definite integral. And notice this definite integral would have been very difficult to solve by applying the rules of integration. In fact, perhaps impossible. So we have a way of solving this. We have a way of solving for this definite integral using power series. All right, so the first three terms is 0.5 to the power of 4 divided by 8 minus 0.5 to the power of 9 divided by 36 plus 0.5 divided by 14 divided by 112. If we plug this into a calculator, add up these terms, we'll get 0.00775,879. This number represents an approximation to the value of this definite integral. And this estimate is accurate to within 10 to the minus 7. That means the error of this approximation is less than 10 to the power of minus 7. So we have a very accurate result for the value of this definite integral by applying power series theory. All right, thanks.